Hello and welcome to another video from our BeamTool tutorial video series. In this video, we want to work together to prepare scan plan for inspecting a weld for creep voids. And we want to build this scan plan based on full matrix capture inspection technique. And the goal is to design a technique that can have a high focusing capability so that we can be sensitive to detecting early stage creep voids before crack initiation. In previous videos, we introduced and explained the concept of point respect function and how the point respect function and parameters that we can read from that, such as focal area, vertical resolution, horizontal resolution, and sensitivity, can help us to assess the FMC technique that we developed to ensure it has a high sensitivity to the type of damage that we want to inspect. And in this case, creep voids are very, very tiny reflectors, and for being able to detect them, we want to design a highly focused technique so that we ensure we increase our chance for detecting these voids. Here you can see that the piece that we are dealing with has 38mm thick and has the weld shape, as you can see, with bevels with 37° and then 10°. And what we want to start with, first I want to make sure that we turn this off so we have a less busy workspace. So the first step would be to load our probe. Again, because FMC full matrix capture is a kind of inspection technique that requires phase array probe. The probe would be phase array. And here, for us to have a highly sensitive technique, we want to use a large aperture probe and high frequency. So here, my choice would be 10L64A12, which is 10 megahertz probe, 64 element, and 0.6 pitch. And I'm going to use SA12N55S wedge that basically goes with that for creating shear beam into the piece. The next step, so I want to give this a name, 10L64A12 and SA12N55S wedge. Okay, now the next step would be to add our FMC beam set. And when we do that, first we choose that we can use all elements in array. We're going to choose the path of shear for this inspection. And we're going to make sure that the imaging box is large enough that contain the weld and also the has area. So here I'm increasing my box from left, right, and match the bottom to match the thickness. Now, when this is designed, now we wanted to see what kind of image we can get based on the aspects of point respect function. So we basically start by going to the simulation. And when we click this, the first thing, the map that we're going to see will be sensitivity, which is a track of max amplitude of point respect function at different location in our imaging domain. And if you are not familiar with this concept, I encourage you to please go to the previous videos when these concepts were introduced. Okay, so this is a kind of map that we get in terms of the sensitivity. And what we know here, just get my cursor back. What we know here is, based on this, is that we have the highest sensitivity and larger value at the bottom left, and the top right, which is the opposite side bevel, we have a lowest sensitivity, which is particularly not a big issue because in many cases, like this case, we can have a two-side inspection. So we want to make sure that we be more sensitive to this side of the skew 90 that is close to the wedge. And here we see that along the bevels, unless we reach very top that is very close to the surface, we have a very good uniform sensitivity, high sensitivity. And if you pay attention to the shadow point respect function, seems like point respect function preview seems like that we have a very good focus, but we can look into that by use point respect function preview. And yeah, we can see that as we move it up along the bevel, left, we have a fairly uniform. Obviously, if we move to the upper side, as expected, now our point respect function will be spread out and low amplitude, but on this side, it seems like it is good. Then we can look into our actual focal area as another metric. Again, the focal area show us how tightly focused our beam is here, and we want to get as small as area we can, as small as a focal area we can. And here again, the key point would be that we have a uniform focal area and a change between 0.12 to 0.9 and fairly consistent along the lower values in the map. So this seems to be a good choice. And last thing that I want to check would be a vertical resolution. And here, obviously, these things are tied into each other. When I have a good focal area, small focal area, my vertical resolution should also be good and uniform. And that's what we see, that more or less the changes are not major. So at this point, these metrics tell me that this can be a very good choice for inspection. And that's what the choice that we went with. And we tried to prove this technique, was evaluate this technique on some creep samples with void from EPRI that had a verified creep, and we tried to use both TFM and phase coherence imaging based on this FMC technique to validate the technique and see how it works. So I'm gonna load the image that we got from this inspection. Okay, so this is the image that we get when we looked at these early stage creep samples with early stage void, and what we noticed was that parallel to the bevel, we have this tiny voids which are parallel to the bevel along the has, which is basically a signature of creep voids. And as you know, what we were really careful about designing this technique was that we have a uniform focal area and vertical resolution along the bevel, and that's what paid off. And it seems like we are sensitive to these, and we detected these ones. And to just make sure that this was a verified sample, this was destructively tested, and in fact was verified here. I show you the destructive results that creep voids were all here parallel to the bevel at the bottom, and that kind of confirms that these are the voids we see. So this is the steps that we went through to make sure that we have a sensitive technique. After we designed this technique and we actually proved it, and when we didn't have access to these samples anymore, the inspection opportunity came up, and we were asked to actually do this inspection on a high energy piping system for one of our clients. But what they asked us to use, because one of our competitors used before, was using a different probe and wedge. The probe and wedge which was used before by our competitor was a small aperture probe with 10 megahertz 32 element but pitch of 0.3, and the wedge which was used with that was SA 10 N55S. So we're dealing with 10L 32A10 and SA10 and 55S. So we were asked by our client to duplicate this inspection and use this small aperture probe and 10 megahertz. With what we knew from this inspection technique and these results, we knew that this is probably not a good choice, because we know that the focusing capability ties into the aperture size. But since we didn't have any we didn't have any good calibration sample because regular side drill holes or notches would not be a good calibration targets to prove this. And also we didn't have access to a verified creep sample. What we could do was to compare these two techniques in terms of what they can do for imaging using point inspect function tools. And that's a very powerful tool now that you realize that you can rely on these without having a necessary calibration verification if you don't have access, especially if you have a proven technique and you want to compare against that. You can evaluate those focal metrics with a new technique, and if it's close to that, then you can expect that you get the similar type behavior. So here I basically we aim to just design the exact same technique with the imaging region and try to compare and see if we can expect to get the similar results or not. So here also, I just turn off the wedge for a second, and here also we add a FMC technique and we keep all the parameters the same. We make sure that we have a match imaging region as we had before. And then at this point, a new tool that we want to introduce at this point will be a compare tool. There is a compare tool here. I can go ahead and, similar to what I did before, I can go and start simulation for this image and this technique. But also what I can do, I can actually directly compare this to the previous technique that I had, because that is essentially my goal here. And I can do that by hit compare here. And when I hit compare, BeamTool asks me that what other technique or beam set I want to try to compare with, and I want to compare with my 10L64A12 and the FMC beam set there. So I click that, and what BeamTool does, split the screen and run the simulation again for both of these cases, and then we'll try to present results with the palette that has the same range from the min and max, so that can be directly comparable. So when this simulation is done, we will be able to directly compare these two maps. So at the top, we see the sensitivity value for the technique with 10L64 and the bottom with 10L32, and we have all the information with respect to our beam sets on the right. So now at the first glance, what I can see is that with the smaller aperture, I don't have as much sensitivity, and that was kind of expected because I'm a smaller aperture probe. And you notice that the sensitivity values are dropping as compared to the larger aperture probe, and actually also along the bevel the sensitivity values are way lower, and also it's not uniform because when I get toward the top bevel I get way more sensitive as compared to bottom. But as you noticed before, that wasn't the case for the top one. So this already show that the weakness or difference in the new technique that was proposed. But we can also look at our other metrics. Let's just go to point response function preview, for instance. Again, you notice that as we move along the bevel, for the bottom one, when we get close to the bottom of the image or to the left, we have basically like a more blurred indication. This is easier to look into that through focal area map. The focal area map is a map that shows the size of our point response function. And again, as expected, you notice that we have a way uniform region along the bevel and the side when we use the higher aperture, larger aperture probe, and the focal area is much smaller, as when you look at the bottom one, the focal area is larger, and again, it's not uniform. Same thing can be seen in when we choose vertical resolution. Again, we see that the vertical resolution is way uniform and smaller when we use this previous technique that we designed. So at this point, when using these tools, we can easily conclude that this technique and using smaller aperture probe is not a suitable technique for this inspection, and it will provide way worse imaging capability or focusing capability as compared to a technique that we have already proven that is working based on our verified samples. And that is the point that we made a decision and we educated our client and everyone agreed that because of these differences that are clear, we need to stick with the technique that was verified. And everybody believed that without any specific experimental validation, that based on these numerical metrics of these values of these metrics, that the choice that we need to make is to go with the larger aperture probe. Thank you so much for watching this video.